Okay, so maybe just as a reminder, we're very close to the end. You only have to have conversations with me or listen to me, either way, for 3 more days. So Monday, Tuesday, and Wednesday, we'll cover sessions 23, 24, 25. And then we have the final exam on Thursday. That's scary. So I'm just trying to wake you up at this point. I will get you the exams. I'm working on getting them to you by Saturday night. Okay, so you all saw the exam 1. I think you have an idea how you're probably doing in the class. If you have concerns, let's talk about them probably early next week. Okay, I mean there's not a whole lot of time left, but yeah, I'm hoping. I haven't graded. Obviously, I haven't graded the exam 2s yet, but I'm hoping that there was after the first exam there was a little bit better understanding of kind of the types of questions that we asked. Okay, this finally formalizes some of the intuition I've been blabbering about for our whole time together. We're going to, now there are 2 of these sessions, so we'll cover 1 today, and then there will be failure criteria 2, right? Because we're going to essentially cover 4 different types of criteria, okay? But we're going to focus on 2 today and 2 on Monday. Okay? Also, please note, sorry, too many thoughts. The lab, all right? Please work on the lab. This would be a good weekend to do it. I think what I did, if I'm not mistaken, is I made the final assignment for session 25 is actually due on Friday. Okay, so we have the 4th of July on Thursday. The final one's due Friday, I think by midnight. Okay, and the labs are also due then, but you don't want to be doing that on the 4th of July / July 5th, right? So try to get it done this weekend as you're studying. The exam is not going to cover the material on Wednesday, okay? So it's Monday, Tuesday. You can kind of tune me out, ask questions on Wednesday, and then we have the final exam. Okay. All right, back to this. So we're going to discuss material testing a little bit and ductility, and then we're going to talk about our first criterion, maximum normal stress for brittle materials, and then we'll talk about maximum shear stress for ductile materials. So this slide you've seen before, okay? We now know we have a gauge length, right? That's essentially the length over which the test is significant, and then we have these little nice little if it's a circular sample, then it would have been turned to a particular radius or diameter. If it's samples like we've been using in the lab, where they're rectangular or they're plate-like, then it's just the radius that was put into the sample. In our case, I guess I didn't really tell you how some of the samples are made. Maybe you care, maybe you don't, but we have wonderful design specialists in the department, and they have essentially a die that they've made, and they can take pieces of aluminum, sheets of aluminum, and they just punch out those samples. So those are the aluminum ones we did. And then we have the paper samples that you saw. Well, you made your own paper samples yesterday. Hopefully that was a little bit fun. All right. And the ones though that you tested to get the tensile strength, those we cut on a laser cutter ourselves. But you can do it. We've done it in the maker spaces, and we have a laser engraver in our lab too. So that's how we've kind of created those samples for testing. Something like this kind of sample, right? That has been turned on a lathe, okay, and those are more expensive to produce than the samples we're producing for our purposes. the purpose of testing is to characterize the intrinsic properties of the material so that we can take these intrinsic properties and then understand how they're going to affect the behavior in a structure. Okay? Said this kind of prior, but to kind of clarify that we have mechanical properties of structures. Mechanical properties of structures, those are the ones where we use the K, the stiffness, right? Or the KT for the torsion, right? Those are mechanical properties. Okay? I have a spring constant, I have a spring rate. Okay? Also this is where the hot spot is. This is where the stress is going to be the highest. This is where the strain is going to be the highest. Those are going to be kind of mechanical properties. Material properties are the ones where I have kind of just digested everything down to an element, and I know what my elastic modulus is for this element. I know what its Poisson ratio is for this element, okay, and I know how it's going to respond. Those are the material properties. Okay? So when someone talks about mechanical properties, typically they're talking about a structure. When they talk about material properties, they're saying, hey, this is the elastic modulus. Okay? So hopefully you don't, I'll mix them up, of course, the mechanical versus material properties, but hopefully at this point this is kind of clear. And tensile tests are not perfect. You saw it, right? You saw it firsthand. You got one, you saw the noise, right? I mean, it's actually quite educational, right? You saw the noise in the sensor, right? It was like, hey, is it 40 or is it 38? Is it 37 newtons? What's going on here, right? So, different material testers are going to be able to give you higher accuracy in the ranges that you're interested in. If you're testing concrete pillars, you probably want to have fairly large load cells. Okay, when I say large, I mean, well, maybe physically large and that they handle, kilonewtons of force. If you're testing biological samples, right, then, you're probably going to have smaller, more, higher precision load cells that can handle, fractions of a newton. Or, and then you get into like atomic scale things, and you're talking like piconewtons. Okay, and we kind of talked about this at the beginning of the class. So you want to use the appropriate machine for the job you have at hand. Okay, and you can get a machine that does very small, accurate readings. That's really expensive, right? Like atomic level accuracy, like atomic force microscopy, that's going to be expensive. You can get a material testing machine that does very high loads and is big. That's going to be very expensive, right? So you want to try, to find the machine that's appropriate for what you're doing. The machines that we have, they're not tremendously expensive. I mean, you're hand cranking them. Thank you, Pasco. I think it's kind of fun to do a hand crank. It's probably the last time you'll hand crank a tensile test. Okay, maybe some of you will never do a tensile test again. There'll be someone in the lab that does it for you. All right, but hopefully some of you will do more tensile testing. Okay, but those machines are a few $1,000s, each one of them. Okay, so they're not like through the roof, but they're not like super cheap either. Even though it has a hand crank, it was like that's so awesome. When I first saw them, I was like, what's up? But you get a feel for it. Okay, so the nominal or engineering stress is typically what we're interested in. We've talked about this before, okay? And the engineering strain is also typically what we're interested in. If you do things with elastomers, the rubbery materials, then you start to get like all kinds of confusion, okay? Because the properties, it's not just an E sometimes. I mean, there's a, right? I can pick a range, any range of any material where I can fit a line to it, right? If I pick a small enough window, it's going to be linear in that range, right? That's linear approximation, right? That's perturbation analysis, whatever you want to call Okay. But when you start stretching a material, to its extent, it's going to potentially have issues with being quote linear. Okay? But in this world that we live, which is 291, things are linear. I mean, even though they're not, like once it's in plasticity, but we don't care, right? Because we developed those material models, right? We said, hey, linearly elastic, perfectly plastic, or linearly elastic strain hardening, right? Linear plasticity, right? Type of model. All right, and we've talked about elastic behavior. We've talked about plastic behavior, okay? And these we've talked about yield and ultimate strength. So I wasn't super careful, but when you were doing those tensile tests yesterday, or maybe 2 days ago, right? What were we really interested in? Were we interested in the yield strength or the ultimate tensile strength? For the paper samples. Yeah, right? I mean, we're kind of like, hey, it's kind of a brittle material. You you might have seen a little bit of, like flattening out, but it's just like, just give me the ultimate tensile strength, right? That's what we're designing for. Okay, ductility, right? We said that you could report it based on percent elongation or the percent reduction of area, and you have necking, okay, and then brittle fracture looks like this. Okay. When you study fatigue, you'll see it'll be fun. Well, maybe it won't be fun. If I'm teaching it, probably won't be fun. But when you look at fatigue, you can actually figure out how something broke or why it broke, the mechanism for failure, just based on looking at the resulting surfaces, okay, of the broken part. So for example, I was a little guy helping this other guy with a consulting job, and he's like, we need to figure out if this bracket failed because of fatigue or because of just a static loading. Okay, so I didn't know what I was doing, but he's like, I need you to. I don't remember what. I think we had a bracket and they had like repaired it, and so I had to like grind down through some of the repair to figure out, okay, what did the actual fracture surfaces look like? And once I had done that, the pro, he looked at it instantly. He said, "Oh, okay, yeah, that was a fatigue." Because what can happen, or I can't remember, it was brittle. I can't even remember. That's bad. But what happens with fatigue? Well, if you have fatigue failure, imagine a crack, and imagine it's opening and closing over and over again. Okay, and the crack is propagating. What happens is that you have this surface that is opening and closing, and it's hitting itself. Okay, and when it does that, it actually smooths it out. Okay, so it's opening and closing, crack is propagating. So if you have fatigue, like you're loading it, it's vibration, it's on a boat, the motor is running a lot, and like this bracket is breaking or shaking, and it's opening and closing. It's nice and smooth, and then the effective cross-sectional area over which stress is being considered decreases, right? Because I've got a crack. Imagine I've got a beam, I've got a crack going down the middle, opening and closing, right? But it's like this, right? Well, at some point, if that cross-sectional area gets too small, the local stresses get too big, and it fails. So what you'll see, classic fatigue failure, is smooth surface, and then when it finally got to be too small, catastrophic, and you'll see a necking or brittle fracture. Okay, so it's for your good to know file. Okay, so now compressive strength of brittle materials is typically higher than yield strength. Okay, so what are we saying? We're saying, and it's kind of intuitive, right? Saying that if I, before you're like, no, don't go this direction on the stress strain curve. I've never been there before, right? Because I never draw those, right? But in quadrant 3, right, you could have a negative stress and a negative strain. Okay, and so if you do, you can have a, I mean, it doesn't, this may be not completely true, but you're going to have essentially this value is going to be, the magnitude of this value down here is going to be typically higher than the magnitude of that value. Okay, that's for a brittle material. Brittle not composite. Well, could be composite, but a brittle material like concrete. And when it fails, it's catastrophic. Okay, typically. And you know, what are some of your favorite brittle materials? Paper. Okay, well, paper is not actually that brittle. It will look brittle in our tensile testing, but wood is, I mean, it can be, it depends, but yeah, okay. What else? Glass, right? So my glasses, some plastics like acrylics, they're pretty brittle. Gorilla Glass is really amazing, actually. You know, it can handle a lot of loading, but what happens when you exceed its ultimate strength?
The whole thing is shattered.
Yeah, the whole thing, like, it's catastrophic, right? And like the Gorilla Glass on your phone, right? You have the cover thing, right? And anyways, yeah, it's pretty cool. Okay, so that's brittle failure. Okay. Now there are multiple theories, right? And there's not one theory fits all. Okay. And so what do we as engineers do? We create safety factors. Right? We talked about that a little bit. We're going to formalize that a little bit today. No, formalize that I guess more tomorrow. But the brittle materials in particular are sensitive. Okay? These are not as forgiving as the ductile materials. And we're going to have two criteria that we use: the maximum normal stress, which we'll cover today, and the Moore failure criterion, which we'll cover tomorrow. Okay. Now, not all metals, like, so this is cast iron here. You don't just think that all steels and all metals are ductile, right? There are a number that do behave with brittle effects. When you take mechanical properties, okay, materials or material, yeah, then they'll cover that. Okay, and we've talked about this, they can shatter, this kind of stuff, right? Ductile materials, we'll think about maximum shear stress, and we'll think about maximum distortion. Okay, tomorrow. Maximum shear stress today. Okay, and there's less variability here. Okay, these theories of failure typically are pretty good at predicting what's going to happen. All right, so which of the following materials are typically brittle and which are ductile? Okay, so that will be a sorting exercise that you get to do. You might want to take a look at the internets. All right, get some examples. Okay, so something about carbon effects, whether materials brittle or not. Okay. All right, so you get to do that. Part 2. All right, maximum normal stress here. So, yes, the fracture plane, this is normal to be applied, or the face of the fracture plane is normal to the direction of the applied load. All right, this is a hint. Right? It's a hint that if I load this material and then it fractures like this, when I have these two surfaces, this is a hint that the fracture is dependent on the normal stress. And that's what you have with the brittle materials. Okay, so normal stress, okay, quite frankly. And what is the maximum normal stress in the system? And how does it compare to the threshold that we set? Okay, it's a pretty simple idea. Now, what if you have a material that's undergoing torsion instead, all right, and it's pure shear? Well, I got to figure out what that equivalent maximum normal stress is to be able to then compare it to tensile testing data. Right? Everything for our purposes comes back to tensile testing. Okay? So here's the pure shear. Okay? And we can take a look, pure shear. I don't care now what that orange point is here, right? I care about where I am on the x-axis, on the horizontal axis, to see if I'm going to fail or not, right? So where those black dots are. So I might have to do a transformation, right? And then figure out what's happening with the normal stresses. And my fracture plane, my fracture line is probably going to be, see this? I have a compressive stress and I have a tensile stress under pure shear. And like we said, the tensile stress is weaker. The tensile strength is usually weaker for brittle material than the compressive strength. Okay, so then that means that it's most likely going to fail along the plane where it's under tension. And that's 45 degrees. Rotate 45 degrees, okay, from the plane that's oriented. So, guess what we're going to do? We are going to break chalk. See, I don't know if I have enough. You have enough. Okay. Here, have a piece of chalk. Okay. I'll try to bring in more chalk tomorrow so that you guys can have some fun. Okay, this one's a little bit short. All right, so I got about half of you. Okay. Apologies. You didn't get a piece. I'll try to show it to you tomorrow. And the people who take care of this are going to be upset with me. All right, so what did we just learn? We just learned that if I apply pure shear here, I care about what the 45, what's happening at 45 degrees. Okay, so if I've got a plane, right, that I've drawn a nice little element on the top here, okay, I care about something that's going to fracture at 45 degrees. So what I want you to do is apply pure shear by twisting, okay, this piece of chalk, and we're going to look at the angle that results. Okay, so now go ahead, look at that. See that? That's 45 degrees more or less. 45 degrees, 45 degrees. So you guys get it? Okay. Now, if I take another piece of chalk, okay, and I apply a bending stress, a bending moment to it, okay, what should we see? Not 45 degrees. What should we see? It's a brittle material, right? So a brittle material is going to have just a clean cut right across. Okay? So let's see. I take this piece, I'm going to do this, right? Look at that. Does that look pretty much flat? Pretty much, right? Give or take, right? So this is what happens when you have a brittle material. Okay? You can just leave the chalk on the chalkboard if you like, or you can take it home as a souvenir. I have someone liked that demonstration so much, they gave me pieces of monster chalk. Like, I've never seen chalk with this diameter. So tomorrow I'll try to remember to bring them in. Oh, you guys are throwing chalk at each other. Okay, all right, that's fine, that's good. I feel the love. All right, so what is the criterion, all right? This is often good when the ultimate tensile strengths and the compression strengths are the same, all right, which can happen. Tomorrow we'll show you the Moore criterion, which is when they're not the same, all right, but this is assuming that they are. And so if they are, here are the Moore circles. And essentially, if I'm looking at it from a Moore circle perspective, I think of this as the field goal criterion, right? As long as I'm in between these two vertical lines on Moore circle, and I can kick the field goal, I'm probably good. All right. So this is the first criterion that we use, maximum normal stress. Now, another way to write this out is on what's called a sigma 1, sigma 2 plot. Okay? And this is not too counterintuitive, but it's maybe a little bit different than what we've been talking about. Okay? What it is that we plot, or first our axes are principal stresses. Okay, sigma 1 and sigma 2. Right? And we can look at different ratios of these principal stresses. But what we just said is that as long as we're in the field goals, right, as long as sigma 1 and sigma 2 are less than the sigma ultimate, or greater, than on this side of the negative sigma ultimate, okay, we're good. So where would we be safe? Where would we not have failure on the sigma 1, sigma 2 plot? Huh? Inside the box, right? So as long as you're inside the box, you will be anything. So this is where we have to map our minds. Okay. So this is a tau sigma plot, right? That's what Moore's circle is. So anything in between these two vertical lines is going to be mapped to be inside this box on a sigma 1, sigma 2 plot. Or a sigma, so this is sigma tau, this is sigma 1, sigma 2. Okay, can you kind of see, can you begin to see this? All right, because what we're going to do is we're going to spend a lot of time thinking about what does failure mean on these sigma 1, sigma 2 plots. So this one's like the easiest one to understand. All right, so I could have, a sigma 1 that's close, very positive and close to sigma ultimate, where sigma 2 is 0. Or I could have sigma 1 being, pretty close to here, and sigma 2 being pretty close to there, negative. But it's just as long as neither of them crosses that threshold, I'm safe. Okay. So that's maximum normal stress theory. Yeah, so failure would happen outside the box. Okay, so here we're saying that the ultimate and the ultimate compressive and the ultimate tensile strength are the same. Okay. Okay, and if right here it's 50 megapascals, there's going to be no failure. Okay, here I have a shear stress. I need to figure out what it looks like, a pure shear stress, right? I got to figure out what it looks like. If I go outside, which I do here, then I'm going to have failure. Okay, and on a sigma 1, sigma 2 plot, right? If I'm the equivalent would be like, say I'm like here, this is going to be sigma 1, this is going to be sigma 2, right? Where am I on this plot? Well, I have sigma 1 as positive 110, oops, and I have sigma 2 as minus 110, right? So I'm going to be out here. Okay, and I'm outside that. And for this situation, right, where I've got a 90 and I've got 30 for tau shear stress, yeah, I have no sigma y. I can use Moore's circle, and then I figure out what my radius is, and I can figure out what my principal stresses are, and I am just inside, okay? So I'm gonna be like over here, okay? So barely no failure. Any questions on this? Yes, Andrew?
So the one in the middle fails?
Yes, the one in the middle fails, okay? All right, because the radius of the Moore circle is 110 megapascals. My sigma 1, if I want to think of it, or my sigma whatever, but this one over here, right? I got one sigma that's going to be a positive 110. I got another sigma that's going to be a minus 110. Either one of those is going to cause me to fail, right? And they're both outside the box. Or, I mean, the point of operation is outside the box, right? That's another way to think about this. You think about, okay, what is my state of operating stress, right? Because again, right, we're trying to relate to material properties. I've got some mechanical structure. And when under normal use or under specified use, right, this is my operating point. I gotta make sure that operating point is within the material limits. Okay. All right, so that is normal stress. There's a question on how to do that. This is a pretty important thing. So let me just go through it quickly so you can do the work, because I don't want to bog you down. I think, yeah, let me just, I've got 1 minute. Okay, all right, I'm just going to take a couple minutes here. And you can watch the videos if you have further questions. Fastest coverage of maximum shear stress theory you've ever seen. What are we saying? We're saying if the maximum shear stress for the material is above a critical threshold, it fails. This is for normal, and this is for many of the ductile materials, okay? And if you saw, remember we said that in the tensile testing of the aluminum samples, some of what I showed yesterday actually, at the end of the class. I said, hey, look at these old tensile tests that we did on the aluminum. You look at the fracture, it was actually at 45 degrees, okay? Well, where do you have 45 degrees, right? When you rotate an element 45 degrees. So these are called Luger lines, okay? I don't know the whole history here, but essentially you can see these bands forming at 45 degrees from normal, and that indicates that you have an issue with failing due to shear. Tresca has his name attached to this, okay, the maximum shear stress criterion. So if I say Tresca, you say maximum shear stress. So what does that mean? That means that we now, before we had to be between the goalposts for ultimate, for the maximum normal stress theory. Here we got to stay within the car lanes, okay? So like you've got like this one up here and this one up here or down here, right? And this down here is actually the positive, but we want to make sure that the maximum shear stress that we're experiencing is underneath, or it's within this threshold. On a sigma 1, sigma 2 plot, it looks like this. All right. So you can go through this quickly. You can watch the other videos that are already there, or you can watch whatever Jeff Hansen, whoever you want, talk about this, or read Pibler's book. How about that? There's a revolutionary concept. Okay. So what you have, okay, is it looks like in the quadrant 1 and quadrant 3, it looks like what you have with maximum normal stress theory. Okay. But then start thinking about what's going on in sigma in the quadrant 4 and quadrant 2, okay? And we begin to see that we gotta have a line that goes between these in order for us to stay safe, okay? And we should cover this maybe a little bit more next week, but there's also a line that's the pure shear line. What's the pure shear line? The pure shear line is when sigma 1 is equal to minus sigma 2. Remember that? Because pure shear, right, we said we have 1 in tension and 1 in compression when we rotated by 45 degrees. So the pure shear line, how would you draw the pure shear line on this? Yeah, it goes from up here. So it goes from the upper left through the origin like that. That's the pure shear line. Okay? So we'll talk about that some more. But here's another example. Again, okay, you're looking to see whether or not you're in the box or not, or whether or not you're in the lanes to see if you have failure. Okay, and here we are also outside the sigma 1, sigma 2 plot. Okay. All right. You can look at the maximum shear stress versus the maximum normal stress. Usually maximum normal stress is more forgiving. It covers a bigger area, not just because the ultimate strengths are often larger than the yield strengths, okay, but also because it's like a box versus a diamond, okay? And then there'll be some more, and we'll have some more fun when we get back together on Monday. Any questions? Okay, that wasn't quite 1 minute. That was like 4 minutes. All right. So that's probably the fastest I've ever done, and probably the most poorly taught as well. All right. Have a good weekend. Oh, sorry everybody. It's looking at you. I don't know why. Sorry. Have a good weekend, and I'll see you on Monday.
Have a good one.
You too.